We are in section 9.2. We are looking at example 5. On example 5, it asks us to identify and graph a polar equation and goes ahead and gives us a heads up. It's going to be a circle. I won't give you the heads up in the test, but right now I will say let's look at the process. Let's think through some of the things we've already seen and talked about, beginning with, it says let's go ahead and transform this to rectangular. When I look at this, it's not something that I look and go, oh, that's going to be a circle. So it's not something like one of the ones we did earlier. We just look at it and go, oh, that's a straight line and it goes through here. So when I see this, I need to rewrite it a bit. If I am going from polar to rectangular, my goal is to take the r's and turn them into x's and y's, and to take anything that's an r or a theta to turn it into x's and y's. I have to keep looking for things I have seen before in this section or sections before, and I'll take it one step at a time. Like right here, r squared. I know that r squared is worth, and I jotted it here, they've got it going on here, x squared plus y squared. And then I know that I still have a 4, but then I have to remember that r sine theta is worth a y. And all of a sudden, just like that, we've gone from polar to rectangular. But we got to keep going and we got to figure out what kind of graph is this. We notice we do have some squares. We have an x square and a y square, which I would check circle. I know it says circle up here, but circle probably would be the nicest one, and let's go for it first. But in doing that, what I'm going to need to do is move my 4y over, and it becomes a negative 4y. And theirs may be more clear. I've lumped all of mine together, got my x squared out front, because I know if it is a circle, I'm probably going to have to complete the square. So x squared is all by himself, he's done. But this y squared has a 4y, so I leave a space. I've already written in it, but I left a space equals 0. I go back here to my b term, which is a negative 4, and I'm going to take my negative 4, and to complete the square, I always divide by 2 and square. I always like to see that number that comes after I take care of this. I simplify what's inside the parentheses because I'm going to need that number. But negative 2 squared is a positive 4. And I need the positive 4 here, but to keep the equation balanced, I have to add it to both sides. So then my next line is to rewrite all that magnificent stuff I just did, and it allows me to rewrite here. I bring the x squared on down, but this y squared minus 4y plus 4 condenses down to a binomial square, y minus 2. Remember that 2 up here? It's always going to happen right there. And then I bring down this plus 4. And we're done. Because in the formula, the equation for a circle, whatever's in there with the x is going to give you the first part of the center right here. There's nothing in there. It's called a 0. Here, I don't use minus 2. I use its opposite just because of the form of the equation. And so instead of putting down minus 2, I put down plus 2. So the center of my circle is going to be at 0 plus 2. There it is. And then my r is not going to be the 4, but it's actually an r squared. So my r is going to be the square root of whatever is there. So my r is 2. And right here you notice that our radius is 2. So from the center, I like to do north, south, east, west. Go up 2, down 2, left, west, and east, and then complete my circle from there. This is a great place for you to hit pause and then do example 6 by yourself with as few notes as possible. When you're done with example 6, go ahead and unpause and then come back, and I'll be starting at the top of page 589. So at the top of page 489, it says, based on the examples we just looked at and some exploration, we are led to some results. These are ideas. I don't memorize these. I know how to work these like we did a while ago. You could write these down on your formula card or memorize these, but these are just a summary. I wouldn't bother with writing them down. But then it does say, there is a method of converting a polar to an identifiable rectangular to obtain the graph. It is not always helpful, nor is it always necessary, and usually a table. That's what I would underline and write down. That a table is going to be created to list several points, And then I would underline that you and I need to know how to check for symmetry. And when you check for symmetry, you can reduce your number of points greatly just by knowing if it's going to be symmetric to, and then you fill in the blank. So some of my notes down here, I just wrote in from college algebra. When you used to check for symmetry, you would test a negative x. And if it turned out to be the same, you would say, I have y-axis symmetry. If it turned out to be exactly the opposite, you would say, I have origin symmetry. We didn't have x-axis symmetry because we were talking about functions, and that would break the rule of the function. And so here we are in polar, and these are the three that I would definitely write down on your formula card. You and I are going to be testing for 3 types of symmetry. Then we're going to go back and do a table based on what we find out on the symmetry to graph some very cool objects that we're about to see on the next few pages. So the 3 that we need to note, this one says points symmetric with respect to the polar axis. And if you look at the polar axis, it kind of looks like somebody we used to know as the x-axis. So if you look down here at the bottom, I would be highlighting, underlining, and then also putting this on my card. If we were in class together, I'd be asking you, what are your different definitions for symmetry? A lot of them might come up. My favorite is that you would take a piece of paper and fold it, and if the object folded identically on top of itself, then you have a line of symmetry, like right here. If we folded this piece of paper down on this line, this blue line and that blue line would lay on top of each other perfectly. The same thing here on this next one. If we fold the piece of paper down the middle, then these 2 lines are going to be on top of themselves perfectly. So this next one is, we're going to look for symmetry with respect to this line theta equal pi over 2. It's the 90-degree angle line, but remember we extend it all the way down. In other words, do I have y-axis symmetry? And then the last one is, like over here, if I had symmetry to the origin, do I have symmetry to the pole? And if I do, the way I like to explain this one is when we had origin symmetry, and the same thing works here, is if we could put a pin right here in the middle and then flick this like you're flicking a little spinner, then this would go all the way around and rotate exactly on top of itself. Then we get to call it symmetry with respect to the origin. But there are 3 tests that go with these. These are the 3 we're going to look at: x-axis, y-axis, and origin, or in this case, we're going to call it polar axis, the line that is theta equal pi over 2, and then looking for symmetry with respect to the pole. So on my formula card, I would write down these 3 tests for symmetry. I would write down test number 1 with respect to the polar axis, and I would put in parentheses x-axis. And I would write down, I will need to plug in theta, I need to plug in negative theta for my theta. That's enough to write down right now. Then I would write down, I'm going to test for the symmetry for the line theta equal pi over 2, and I would put in parentheses the y-axis, and I would write down in my notes that I'm going to put this thing, pi minus theta, in place of theta, and then we're going to manipulate it, and if it comes out the same, then we will declare that it is symmetric with that line. And then finally, you're either going to plug in r or negative r. So the last thing you're writing on your formula card is that when you test for the symmetry of the pole, parentheses, the origin, then I need to either plug in r or negative r for the r, and if it turns out the same, then I declare it is symmetric with respect to the origin, or I can plug in this, theta plus pi, in place of theta, and if it comes right back to the original equation, then I still get to declare that I have symmetry with respect to the pole. So we are about to look at many different items. You're going to hear things called a cardioid, a limacon with an inner loop, without an inner loop. And you're going to look at some things, and I'll come back in a minute and talk about arrows. There are a couple we are going to not do. We're going to skip those. But you'll notice in your notes which one we are going to do, which ones we are going to do, and which ones you're going to need to know for the next test. And so the 3, this is a really important statement, and you're going to hear it in his videos. The 3 tests for symmetry given on the previous page are sufficient for symmetry, but they're not necessary. Keep that in mind, ponder it, think on it, make it make sense in your brain. In other words, an equation could fail these tests and still have a graph that is symmetric with respect to either the polar axis, the line theta equal pi/2, or the pole. It gives us an example and it shares that with us. And when you're listening to his videos, hear what he's saying about sufficient and not necessary. They're not necessary conditions. Listen to his videos, and I'll pick back up with you at the end of this chapter. Actually, the end of this section.